All right, welcome to the deep dive. We've got this really interesting stack of source material you sent over. All notes and explanations focusing on circles.
That's right.
Now, most people think, yeah, I know what a circle is. You see wheels, clocks.
Yeah.
They seem simple.
They do. They're everywhere.
But our mission today with this deep dive is to get past just, recognizing them.
Yeah.
We want to dig into this material and pull out the key ideas, the geometry behind it, so you really get a handle on it.
Sounds good. And the source material starts right with the core definition.
Which is?
It defines a circle based purely on distance. It's the complete set of points, all lying in the same plane.
Okay.
That are exactly the same fixed distance from one specific point in that plane.
So it's not just round. It's that precise constant distance.
Exactly. You could think of it as the path or locus of a point moving so it always stays that exact distance away from, well, the center.
So the source names these parts. That fixed point is the center.
That's the center.
And the fixed distance itself.
That's the radius.
Okay. And the actual curve, the boundary.
That's the circumference. Center, radius, circumference, the building blocks.
Got it. Simple enough. Now, the material also talks about lines within the circle connecting points on that circumference.
Right. If you draw a line segment between any 2 points on the circumference, that's called a chord.
Any 2 points?
Any 2 points. But there's one very special chord the source highlights.
Let me guess. The one through the middle.
Exactly. The chord that passes right through the center, that's the diameter.
And the notes mention something specific about its size, right?
Yeah, it points out the diameter is the longest possible chord you can draw in any circle.
Makes sense visually.
And it's always exactly twice the length of the radius. 2 radii end to end.
Okay. Diameter, longest chord, twice the radius. Now, what else did these sources say about chords? There was something interesting about how they relate to the center.
Yes, this is quite neat. It says if you draw a line from the center of the circle and it cuts a chord exactly in half, bisects it, and that chord isn't itself a diameter, then that line from the center must hit the chord at a perfect right angle.
Wow. Okay. Perpendicular. That's not immediately obvious.
It isn't. And importantly, the reverse is also true according to this material. If a line comes from the center and is perpendicular to a chord,
then it must cut it exactly in half. It must bisect it.
Precisely. It works both ways. Super useful properties for sort of figuring out the internal geometry.
And this relates to another point in the notes, doesn't it, about the chord's size versus its distance from the center.
Yes, there's an inverse relationship described. Basically, the longer a chord is,
the closer it is to the center.
Exactly. The closer it has to be. And the shorter the chord, the further away it is out towards the edge.
You can picture that. A tiny chord near the circumference, a big one slicing near the middle.
It gives you a good feel for how things are structured in there.
So these rules, these properties, they all build up, which leads to maybe the biggest idea in this material about what makes a circle, well, a circle, its uniqueness.
That's a fundamental point raised here. The source states there is one and only one circle that can pass through any 3 specific points.
Okay.
Provided those 3 points aren't all lined up in a straight line, they have to be non-collinear.
Just one circle. Why? How did 3 points lock it down like that?
Well, think about those chord properties we just discussed. If you have 3 points, say A, B, and C, not in a line, you can think of the segment AB as a chord and BC as another chord.
Right.
And we know the perpendicular bisector, the line that cuts a chord in half at a right angle, must pass through the circle's center.
Okay, so the perpendicular bisector of AB goes through the center.
And the perpendicular bisector of BC also has to go through the center.
And since 2 distinct lines can only cross at, well, one single point,
that intersection point has to be the center. It's the only possibility. And once you know the center, the distance to A, B, or C defines the unique radius.
So those 3 points completely define the circle, its location and its size.
Wow. It really shows how these geometric ideas connect the definition, chords, bisectors, all leading to this unique identity.
Amazing. Such a common shape, but these precise rules underpinning it all, laid out in this source material. Okay, so let's quickly recap this deep dive for you.
We started with the core definition, all points equidistant from a center.
Right, giving us the radius and circumference. Then chords, with the diameter being the longest, twice the radius.
We saw that key relationship. The line from the center bisecting a chord is perpendicular and vice versa.
And that inverse link. Longer chords are closer to the center.
Leading to that powerful idea, 3 non-collinear points define one, and only one unique circle because their perpendicular bisectors pinpoint the center.
It definitely makes you see them differently. So here's something to chew on. Now that you've got this deeper understanding from the source material, that precise distance rule, the chord behaviors, the uniqueness from 3 points, where might you spot the consequences of these geometric facts, maybe in unexpected ways, in the world around you? Something to think about.